Okay, so I've just downloaded this PowerPoint from your Moodle site. It's got, obviously it's got the topics that I'm going to talk about, and it's also got notes down the bottom. Um, um, so don't be scared to go. Just have a look at those notes of what I'm going to say or the main points that I'm talking about. Okay, so we'll talk about scanner. I'm going to talk about the hardware, a little bit of software, but mainly the hardware of the scanner. And I'll also talk about safety. Okay, so they're the two things that we spend most of the time on today. We'll talk about, I will, if I have time near the end, maybe 15 minutes or something near the end, I'll talk about scanning protocols, talk about pathology, and advanced techniques, but they won't be on any tests this year. Okay, so they'll be on a test next year. And obviously we'll go through a lot more detail next year. So I like to just go through that and give you an idea of what sort of things the scanner can do. But it won't be tested, and I'll remind you when I get there. Okay. So you can hear me. I'm assuming you can see my slides. I was going to say something else, but I'll think about it later. Okay, so that's the MRI machine that we'll be talking about. Now we know that MRI doesn't use radiation. Okay, so it's a very safe machine. We use it for clinical, it's got a very good clinical functions. It's also got a lot of research functions because it can do things that other modalities don't do and get a lot of different types of information that you're going to be able to see in the next, through this year and next year. Because it doesn't use radiation, doesn't mean you're not going to have hazards, doesn't mean it's not going to be, it's not going to be safe all the time. So when you're working in MRI, you have to be extremely cautious and know what those safety implications are. You've got a scanner there. That's the scanner that you're looking at is a 1.5 Tesla. This photo is a little bit older. Let's say we can take that bed out and take that antenna out, that little cage that's in the middle of the ball, okay? So we'll take the bed, we'll take that cage out. What we're left with is this big donut thing. That's a very, very strong magnetic field, okay? So if ever you've seen it, if ever you've experienced it, that is the one we're looking at, 1.5 Tesla, but most of them that you'll be using in your clinical practice are 3 Tesla, which is incredibly strong, okay? And so that has implications on what can happen and what you can take into the machine and what patients can go into the machine, okay? There's another picture. We've also got a table. We've got that head coil, or we've got the bottom of that head coil, and we've got the bore of the magnet. The length of the bore is 2.5 meters, so it's 2.5 meters deep, okay? The diameter of the bore is 0.6 meters. This is an older machine. Some of them go up to 0.7, and there's one type that go up to 0.8 of a meter wide. This means that the machines can be very claustrophobic. So we have to be careful. So there's some patients that just can't have the scan because it's too claustrophobic, okay? And we have to give them sedation and things. If we go back to this scanner, we've got what's called a head coil, okay? So a coil is just an antenna. We know that, oh, I know what I was going to say. Can someone tell me, have you had physics lectures with the Manse yet? or any sort of MRI physics lectures? Can someone just write a note or yell out whether you've had physics lectures yet?
Yeah, we had physics on MR.
Okay, have you finished it all, or are you still going?
Halfway. We started this semester.
Okay, and that's with Amans?
Imans has retired. I think we have Karen now.
Right, okay. Okay, excellent. Thank you. Very good, very good. Right, so what they would have told you then is that this is a head coil, okay? So the machine is a very strong magnet. It's never switched off. It's always on. It generates the magnetic field that's needed for the process. It's also, the bore also has other functions. So you would have been told that the bore can put in radio frequency, okay? That radio frequency goes to the head, and then it's manipulated, or you listen to water and fat protons, and then that signal is detected by the coil. Okay, and I'll give you my little rundown. Oh no, you would have heard it in your MRI physics. Okay, so so you've got a bore of the magnet that has a very strong magnetic field. It puts in the radio frequency to the patient, and the antenna listens to that radio frequency. And it also has what's called gradients inside. So the gradients manipulate the strength of the magnetic field just in a short space, about 50 millimeters inside the magnetic field. Okay, so there's two things. There's a couple of things that happen inside there. So you've got those gradients manipulate the magnetic field so as to spatially locate the signal. Okay, we know that fat and water give off a different signal depending on what the hydrogen is combined with. So if the hydrogen is combined, we scan hydrogen. We know that if the hydrogen is combined with oxygen, it will make up water. Okay, if the hydrogen is combined with carbon, it will make up fat. Okay, because that's what fat is. But we're only imaging the hydrogen protons. We only care about hydrogen protons. Those hydrogen protons will behave differently depending on what they're combined with. Okay, so as I say, if they're in fat or if they're in water, they'll behave differently. So we'll flip those hydrogen protons, and then they'll realign with the magnetic field because of the strength of the magnetic field. We're sitting here, all our hydrogen protons are random. Once we put the patient inside the magnetic field, they all align with the magnetic field. We put in that radio frequency, that flips those hydrogen protons. It might flip them 90 degrees, it might flip them 180 degrees, it might flip them 5 degrees, and then they relax back. Okay, as they relax back, the machine detects a signal. Okay, so that's the radio frequency coils inside the machine. Put in the radio frequency to flip those hydrogen atoms. Okay, the gradients, they change as we're scanning. So when that signal comes out of the brain, those gradients help us spatially locate that signal, tell us where in the brain that signal comes from. Okay, and then of course we've got the main magnetic field that aligns those protons with the magnet. Okay, otherwise they're just completely random as we are now. So we've got coils, we call them coils, and from now on you won't, you'll refer to them as coils because you know what we're talking about. So coils are antennas, okay? So what happens is the machine puts in radio frequency to the brain, and then that manipulates the hydrogen protons, and the coils listen to that radio frequency. Okay, so we've got different head coils. We want those coils to be as close to the body part as we can. So if those coils, if we're doing a head scan, we want coils that are going to be very close to the head. If we're doing a spine scan, we want coils that are going to be very close to the spine. Okay, we don't care about anything else. We only care about what we're imaging. If we're doing a wrist scan, we want coils that are very close to the wrist. Okay, we don't want coils that we don't want to do a head scan, use a head coil for a wrist scan, because that head coil is too far away. Okay, once those protons, hydrogen protons in the wrist, if you put a wrist in there, once they relax back and they give off their signal, or that signal is detected, you lose too much between that wrist and the head coil. You lose too much signal. Okay. There's also a coil inside the machine, and that's called a body coil. Okay, so we can actually scan without our head coil. We can just scan a patient lying on the table. The body coil inside puts in the RF to the patient, and then it will listen to that RF. Okay, the trouble is that if we use the body coil, again, the signal is too weak between the brain and the body coil, and you're going to lose a lot of signal. Okay, so that's the purpose of having a head coil, a spine coil, and a wrist coil, and a knee coil, and everything else that we have. They're called local coils. Perhaps we have surface coils which go wrap around a knee or wrap around a limb. Now, I've just said that the body coil puts in the radio frequency, and the head coil listens to that radio frequency. Okay, we're going to say that head coil is a receive-only coil, because it only receives the radio frequency signal. It doesn't detect the radio frequency signal. It only detects and receives the radio frequency. It doesn't transmit the radio frequency. Okay, and that's what most coils are. Most coils are receive-only coils. We do have what's called a transmit-receive coil. So we do have coils that transmit the radio frequency and they receive the radio frequency. Okay, so they're called transmit-receive coils. Of course, we can use a lot less energy if we're transmitting and receiving radio frequency just immediately to the patient, rather than transmitting from the bore of the magnet. Okay, so that's going to be a lot more homogeneous, but don't stress. It definitely has its advantages with transmit receive. Okay. Okay, so we know this is a lumbar spine. We know that this is fat sitting right next to the posterior to the patient. We know that this patient is lying on a spine coil. Okay, so the signal immediately next to the spine coil is very bright. Once we go further away from the spine coil, we start to lose signal. Okay, and so this slide is just a good example, I like, of how you need a coil that's right close to the patient's back when we're doing a spine, and a close to the patient's head or close to the body part that we're imaging. Okay. The further away from that coil, the less signal we have. Okay. So that's my little introduction onto the hardware that we use in MRI. Okay. And I take it, of course, if you want to ask questions, yell out. Just yell out. If you want me to go slower, go faster. I'm going pretty slow at the moment. Yeah, if you've got any questions, if you want anything, if you want to put something in chat. I don't think I'll hear it, but yeah. Right. So that's a little introduction into the equipment that we use. Now we're going to get on to the safety part of the talk. Okay. So we've got 3 parts to MRI safety that we have to be aware of. The first part, and I've briefly introduced these, the first part is the main magnetic field. The second part is the time varying magnetic fields. And the third part is the radio frequency fields. Okay. So when we're talking about implants, when we're talking about procedures, and we're thinking about safety, they're the 3 aspects that we have to consider whether these implants are safe or not. So the main magnetic field is the primary magnetic field. It's a superconductive magnet. It's always on and the force is always constant. It doesn't change, okay? So at 2 o'clock in the morning, at 4 o'clock in the afternoon, at 9:21 in the morning, that magnet is always on, okay? And it's an incredibly strong magnet, okay? The force in there, the magnetic field in that magnet and around that magnet will not change. It's called a static magnetic field. It will not change, okay? It's always on. So that's called a static magnetic field or a primary magnetic field. It's a superconductive magnet, okay? There's different types of magnets that we use. Nearly all magnets, in fact, I go out on a limb and say all magnets that you'll use and in clinical practice will be a superconductive magnet. It's always on and the force is always constant. It never changes. Okay, so what happens? What does that cause? Well, the first thing that happens with the main magnetic field is it causes projectiles. Okay, I think we'll see a little video in a couple of slides to show how if you've got a magnetic object, okay, and you put that magnetic object, ferromagnetic object, into the machine or near the machine, or not even near the machine, in the room, there's a chance that magnetic object will travel towards the machine, okay? And the closer it is to the bore of the magnet, the more it will become a projectile, or we say a projectile or translational force, okay? And we'll show you exactly where in the machine that's going to be strongest or weakest, okay? It'll also torque, okay? So it'll also have a torque force on that ferromagnetic object. So that object, okay, it will go into the machine and be a translational force towards the machine that's over here. It will also try and turn, okay? So that force is what's called torque force. So it will turn. If that was a ferromagnetic object like a ferromagnetic stent in someone's blood vessel, and we put that person inside a magnetic field, of course that stent is going to torque and push against the magnetic field or push towards the magnetic field, have the chance of going through the blood vessel and dissecting the blood vessel. Okay, so we've got translational force and we've got torque or turning force on that object. We've also got interference of with other electrical equipment. So if we took a mobile phone in the machine, if we took a digital watch in the machine, there's a good chance that the machine will break the mobile phone and the digital watch. Okay, because we know that strong magnetic fields set up a current, and that will set up electricity in the circuitry, and that machine will break. Okay, so yes, whilst that's tragic for radiographers who take their mobile phones into the machine, it's also tragic for patients who might have a mechanical implant inside their body. Okay, and the machine's going to change the functioning of that magnetic or mechanical implant, and cause a lot of damage, possibly death. Okay. So that's why we're having this chat, this little chat. Small electrical potential. So this point applies to nearly all points that we're going to discuss with safety, in that we know through our physics in university and hopefully year 12 or below that if any conductive material experiences a change in magnetic field, it sets up a current. Okay, so if we have any circuitry, namely blood in our bodies, okay, so blood is electric material like water. It conducts electricity. We know that water conducts electricity. Obviously, we know blood conducts electricity as well, okay? So if the blood travels, let's say we've got a patient inside this machine, make space for the patient. We've got a patient inside this MRI machine. We know that it's 3 Tesla at the isocenter, okay? We know that at the bore of the magnet, it's actually a little bit more. So it's about 3.4 Tesla at the bore of the magnet, okay? And then it drops off, drops off, drops off. The strength of the magnetic field drops off till the door, okay? So if we've got a patient inside the magnet, their aorta is traveling or is conducting blood, okay, or blood's going through the aorta. It's traveling from the isocenter out to the iliacs, which is at the bore of the machine. It's experiencing that blood, as it's traveling through the body, it's experiencing a change in magnetic field. So it's going to set up a current, okay? Anything that experiences a change in magnetic field will set up a current. So when the heart's moving, the heart's beating, and the electrical impulses are beating, they're going to set up a current because they're moving with respect to the main magnetic field, okay, or the static magnetic field. So they're going to set up a current, okay? That current is very small. It's not of any clinical significance to the patient, but we will see it on ECGs, okay? So usually if I'm giving this talk to scientists or giving this talk to other professionals, I'm not really too worried about it. But because we'll be using MRI machines, you guys have to understand that if the doctors are looking at an ECG machine and they see the changes, it's because of the current in the patient traveling along the bore of the magnet, okay? Or cells in the body, conductive material in the body that's experiencing a change in magnetic field, because outside this isocenter, where we're scanning, there is no change in the magnetic field. The magnetic field is completely homogeneous. But once we leave that little center of the magnet, we start to experience a change in magnetic field, okay? As conductive material travel and experience that change in magnetic field, they will set up a current, okay? I'll put that back where it was. All right. So also, you would have noticed that we have fringe fields. So the magnetic field doesn't just stop at the bore of the magnet. The magnetic field continues on until the door, okay? So yes, it gets a little bit weaker, but it's still at the door. There is still a chance that there is still a small magnetic field that gets greater and greater and greater as we travel towards the magnet. So that's called a fringe field, okay? You could say it's a byproduct of this magnet sitting in the middle of the room. We don't want it out there, but we can't stop it. All right, we obviously have such a strong magnetic field in the middle of the room. We try and we try and reduce that fringe field and keep the magnetic field as tight as we can to the magnet, but that causes safety implications in itself that we'll discuss in a minute. We also have what's called shielding. So we have active and we have passive shielding. So what shielding does is that tightens the magnetic field. So we do have more of the magnetic or less magnetic field outside the bore of the magnet. Okay. We need the magnetic field to be within the room. If we didn't have shielding, that magnetic field would extend outside into the control area. Okay, and obviously that would cause problems with our equipment outside the control area. So we have processes that are called shielding, and that shielding is designed to do a couple of things, but mainly to tighten that magnetic field to keep it within the magnet. And also the shielding helps keep that magnetic field as homogeneous as possible at the bore of the inside the isocenter of the magnet. Okay, so that's where we're scanning. We don't want any changes in that magnetic field. It's got to be completely 3 Tesla inside that small area, about the size of a basketball, inside at the isocenter of the magnet. Okay. Okay, so this is what's called a spatial gradient. Okay, so we've got a machine. We're looking at the machine from the top of the scanner. This is the isocenter of the machine. Okay, so we've split the room into 4. We've got the bed that lies in here, inside the scanner. We've got exactly the same over this side, and we've got exactly the same over this side. Okay, so essentially we're looking from a bird's eye view of the scanner, and we've cut the scanner into 4, the room into 4 quadrants, and we're just looking at one quadrant. Okay, so we've cut the top of the machine off horizontally, and we're looking from bird's eye, and we're seeing just this corner of the room. And we know that the corner of the room is exactly the same as the front of the room. The other corner, it's exactly the same as the 2 corners in the back. Okay. So all we have to do when we're looking at the spatial gradient is to look at the corner of the room. If we're looking from the roof, we've cut the front left corner out. We know that this is the isocenter. 0, 0 is the absolute isocenter of the machine. It's the middle of the machine. Okay, and as I said just a little bit earlier, that isocenter is completely homogeneous. Actually, I beg your pardon. I've read this. 0, sorry, the isocenter is here. I'm not sure why this diagram's a little bit different, but that's okay. So the isocenter is at 0 and 0. So it's right at the middle of the machine. Okay. So what's happening is, again, we've cut the machine in half horizontally, or the room in half horizontally. We're looking from the top. This is the front left. The bottom left is exactly the same as the front left, and the back is exactly the same as well. So this is the isocenter. So this is exactly the middle where the field is homogeneous. When we do scanning, we can't afford the magnetic field to change. The magnetic field has to stay exactly 3 Tesla. Okay, so there is no change in magnetic field. So we don't have any lines here. We don't have any contours that show that there's a change in magnetic field. And to explain that a little bit more, these contours are called Tesla per meter. Okay, so they describe the change in magnetic field over the distance. And I'll explain why that's important in a minute. So this magnetic field changes at 0.1 Tesla per meter at this location. Okay, so you go a little bit further from the isocenter. This magnetic field changes at 0.3 Tesla per meter. Okay, so we can imagine that this scanner, the strength of the magnetic field becomes a little bit stronger. So if we just look at the Tesla, okay, we're not looking at the change in magnetic field now. We're just looking at the Tesla. So we can say that this is 3 Tesla. Then it becomes maybe 3.1 Tesla, 3.2 Tesla, 3.3 Tesla at the bore of the magnet, okay, as we come outside of the magnet, and then it becomes 3.2 Tesla, 3.1 Tesla, and it goes from 3 Tesla down to 2 Tesla very quickly, okay. So that change in magnetic field is very rapid at this location. Okay, and then it goes from 2 Tesla to 1 Tesla, which might be out here somewhere, very slowly. Okay, so we see our contours start to spread out again. Okay, so our Tesla per meter scan starts to spread out a little bit more down here. But because we're going from 3 Tesla or 3.4 Tesla to 2 Tesla in a short distance, then we're going to have a high, what's called Tesla per meter, a high change in magnetic field in a short distance, okay? And that change in magnetic field is greatest at the gantry, at the side of the gantry where the buttons are, okay? So we have a very small change in magnetic field because here it's changing from 0 Tesla, it's changing from 3 Tesla to 3.4 Tesla over a relatively large distance, 0.6 of a meter, okay? But here it's going from 3.4 Tesla to 2 Tesla over a very small distance. So of course there's going to be a large change in magnetic field in this area. Okay, so there's going to be a large change. If there's a large change, then obviously we've got 15 Tesla per meter change in magnetic field at that location versus, which is the greatest, versus 10, 7, 5, 3. So they're still very strong where the magnetic field is changing. And then it starts to get 1.53 Tesla. So the change in magnetic field down here, as the machine's going from 2 Tesla to 1 Tesla or even less, 0.5 of a Tesla, the change in magnetic field is much less. And much less up here because it's going from 3.4 Tesla to 3 Tesla. Okay, does that make sense to everyone? It's quite a hard concept to understand, but once you understand it, but it is very important. Okay, when we talk about magnetic safety, and it's caused by the spatial gradient. So it's caused by that magnetic field staying on all the time. It's the change in magnetic field over the change in distance. Okay, so the change in magnetic field is in Tesla and it's per distance, so it's Tesla per meter. Okay, so why do we care? Who cares? There's a change in magnetic field. Don't we care about the magnitude of the magnetic field, 3 Tesla, rather than change in magnetic field? Okay, so we care because the translational force on my ferromagnetic stent or ferromagnetic object that I'm stupidly going to take into the room, the translational force will be greatest where the change in magnetic field is greatest. Okay, so we have so if I was to take this ferromagnetic object into the room, it would have a small pull over here. Okay, not just because the magnetic field is less, so it might be 0.5 of a Tesla over here, but because the change in magnetic field is less over here. It's only 0.1 Tesla per meter, which is a small change. It might be enough well, it probably would be enough to really feel a strong pull of this magnetic field. Okay, but it's, if you compare this area to this area, okay, we know that this area, if you put our ferromagnetic object next to the buttons of the gantry, okay, so we're looking at the gantry from outside, this is the opening of the gantry, okay, or the opening of the bore of the magnet. If you put our ferromagnetic object here, that's going to experience the greatest force in the whole room because it's up to 15 Tesla per meter. That's the change in magnetic field, which is relative to the force, the translational force on this object. Okay, so what about if I put this ferromagnetic object at the isocenter or in line with the isocenter, okay, straight down the bore of the magnet, where the change in magnetic field was only 3 Tesla per meter. Sure, the magnetic field is probably, the magnitude of the magnetic field is probably 3.4 Tesla. So the magnitude is greatest, but the change in magnetic field is not as great. So the force on that ferromagnetic object in the middle of the machine won't be as great as if it was at the maximum position of the maximum spatial gradient, which is where the maximum change in magnitude of the magnetic field. Okay. So another thing that we're going to just add here, I'm going to add here, is called the force on a the translational force. So we're going to say the translational force on a ferromagnetic object is equal to, it's called the force product. It's equal to the change in magnetic field, and we're going to say that's Tesla per meter. Okay, so we've talked in Tesla per meter up here. So it's the change in magnetic field times the magnitude of magnetic field. And that is in Tesla. Okay, so the translational force on an object, on my ferromagnetic pen, it's called the force product, okay? And it's change in magnetic field measured in Tesla per meter times the magnitude of the magnetic field. So if we've got a 1.5 Tesla machine and we put my ferromagnetic object here where it's going to experience, let's say, we'll put it here where it's going to experience 3 Tesla per meter, okay? So the force product, the total force that's incident on that ferromagnetic object will be, we're going to say 1.6 because it's a little bit more than no, let's keep it simple. 1.5, okay, times 3. So that's going to be 4.5. And it's in Tesla squared per meter. Okay, I'm not going to bother with that. Can I do that? Tesla squared, and then put it up a little bit. Tesla squared per meter. Okay, so if we've got our ferromagnetic object, we put it inside at exactly this location. Okay, so it's going to experience 3 Tesla because it's 1.5 Tesla. Okay, because that's the magnitude of the magnetic field at that location. And it's the change in magnetic field, so it's going to experience 4.5 Tesla squared per meter is going to be the force product. Okay. If we had a ferromagnetic object in a 3 Tesla, then we're going to have 3 Tesla per meter times 3. So it's going to experience 9 Tesla, not a force product of 9 Tesla squared per meter. Okay, that makes sense. If we put our magnetic field, if we put our ferromagnetic object in a 3 Tesla up here, where it's going to experience, let's say it's going to experience 10 Tesla per meter, that location will be about, let's guess that's a 2.8. It's going to experience 2.8 Tesla. Okay, so its force product will be 2.8 Tesla times 10 Tesla. So that's 28 Tesla per meter. Okay, does that make sense? So it's going to have maximum force right at that dot. Okay. Okay. I think we can move on. Just the last thing is, that's the force product. So that governs the translational force on this ferromagnetic object. What about the torque? I mentioned the main magnetic field also governs the torque, or the turning force on that object, on that stent that's going to be, on that stent that's going to be pushed against the vessels, the blood vessels. Okay. So the turning force is relative to the strength in magnetic field. It's not relative to the change in magnetic field. The turning force is relative to the strength of the magnetic field. Okay, so the higher the magnetic field, the more torque force will be on that object. Okay, and it also depends on the object. So if you've got a spherical object, there's obviously going to be no torque force. Okay, so you've got a ball I've got a little camera here. I don't know why, because it's useless, but I've got a little camera here that's like a ball. Okay, the torque, the translation force on that camera will be very strong. The torque force on that camera will be minimum because it's spherical. Okay, so if you put a ferromagnetic tennis ball into the machine, you won't have any force, translational force. You won't have any torque force. If you put a ferromagnetic pen in, okay, you will have a greater torque force because of its object, because it's going to have different poles. Okay. All right. So what we've covered so far is the main magnetic field. We've only talked about the main magnetic field that's caused by the superconductive magnet. It's causing projectiles. It's causing turning force. It's causing interference with other electrical equipment. It's setting up small electrical potentials, and it has fringe fields. Okay, it doesn't just stop at the bore of the magnet, it carries on until the door. okay? And that's all because of the main magnetic field that's always on. It never changes amplitude. It's always on, okay? Now we're going to switch tacks. We know that that's not the only thing that causes our pictures. We know that we have what's called a time-varying magnetic field, okay? So what that does is we know that the main magnetic field aligns those protons, aligns those hydrogen protons along the bore of the magnet. Okay, that's its job. The time-varying magnetic field alters the magnetic field inside the magnet very, very quickly. Okay, and the gradients I mentioned earlier, the gradients do that. So the gradients change the magnetic field, and it superimposes a new magnetic field onto the existing magnetic field. Okay, so when I say that, I mean you've got a bore of the magnet, and you know that that's 3 Tesla at the isocenter. Okay, and where we're scanning is completely homogeneous. It's going to be 3 Tesla. The gradients superimpose a magnetic field over that. So if we're just looking at one plane, we know that it's 3 Tesla in the middle, and it's going to be, at some stage, it might be, it'll be 2.99 Tesla, and it'll be 3.11 Tesla, or 3.01 Tesla at the other side. Okay, so it'll superimpose a magnetic field, and it'll change the magnetic field in that plane. And then it'll flip. So it'll go from 2.9 to 3.1, and this area will go from 3.1 to 2.9. And then it'll flip again. So if I'm a little atom here, okay, next to the isocenter, I'll experience 2.9, 3.1, 2.9, 3.1, 2.9, 3.1 very, very quickly. So a small change in magnetic field is actually a lot less than 0.1, but a small change in magnetic field very, very quickly, okay? And the reason it does that is when that signal comes out, it tags it with another magnetic field, okay? And so it can spatially locate it. It can work out exactly where in that magnetic field that signal come from, okay? So to do that, it changes the gradients inside the machine, change the magnetic field. And this hydrogen proton, or these cells with hydrogen protons in them, and oxygen and hydrogen and every other proton, they experience a change in magnetic field. So even though they're not moving, they experience a change in magnetic field. We know that the change in anything that experiences a change in magnetic field sets up a current. Okay. So that change in magnetic field induces currents in nerves, blood vessels, and muscles. Okay, and that's called peripheral nerve stimulation, PNS, peripheral nerve stimulation. Because we know that we're lying in the machine, the nerves, we know that the nerves work by inducing current. So if I wanted to move my hands, the nerves would send an electrical impulse down into my hands. We know that, okay? So if we change the magnetic field around the nerves, these nerves are experiencing a change in magnetic field, so they'll set up a current. And that current will cause my fingers to twitch, okay? Or it'll cause maybe pins and needles. If that current happens in my eyes, it can cause the patient to see stars in their eyes. Happens in the patient's eyes, not mine, obviously. Okay, so the patient may experience stars in their eyes, and that's called magnetophosphenes. Okay, all because those optic nerves, they're experiencing a change in magnetic field. They're not at the isocenter, they're a little bit off the isocenter. They're experiencing a change in magnetic field. So we know anything that experiences a change in magnetic field sets up a current, okay? The more that magnetic field changes and the faster it changes, so the less time between changes, the more voltage, okay? So the voltage that is induced in the nerves is proportional to the change in magnetic field, okay? The more the magnetic field changes, the more voltage, and it's proportional to, or it's inversely proportional to the change in time. So if it takes a longer time to change, it's not going to get as much of a current. If it changes very quickly, the magnetic field changes very quickly, it's going to increase the current or the voltage that's induced in that in those nerves. Okay. Fortunately, there are limits. So the Food and Drug Administration, don't stress, say that you can't cause more than 6 Tesla per second a change in magnetic field. Okay, if you do that, the machine will calculate that at the start of the sequence when we press the go button, and it will say, I'm not doing that sequence, because the change in magnetic field experienced very quickly in the body will be too fast. Okay, you experience a change in magnetic field too fast, you exceed the threshold, the machine says, I'm not scanning that because it's not safe. Okay, so that's our little catch. The other thing too is the acoustic noise. So when we change the magnetic field, this causes a very strong noise. It's a very loud noise. So everybody that's in the room while we're scanning must wear earphones. Okay, and that's because of the gradients moving while they're changing the magnetic field. The last thing we'll talk about just before a little break. So we'll recap quickly. The main magnetic field, okay, so we said that the main magnetic field is on all the time. It causes forces, projectiles, torque, and interference with other electrical equipment. That's caused by the main magnetic field. It causes electrical potentials in moving cells, moving material, moving superconducting material, okay? And it has fringe fields. So we're just talking about the main magnetic field here, and we're talking about the static gradient, the spatial gradient, caused by the main magnetic field. Then we talked about the changing magnetic field and how that sets up a current. Okay, and we have a changing magnetic field mainly for spatial localization. Also gradient echoes, but we'll leave it simple for now. The third thing that we have to worry about is radio frequency fields. So I mentioned at the start that radio frequency fields, we put in energy of those, that we know that those atoms are precessing. Okay, so they're wobbling around inside the magnetic field, and they are aligned down the bore of the magnet. If we put in little packets of energy, exactly the energy that they're precessing, or the frequency that they're precessing, we're going to flip those protons, and we're going to make them all go in the same frequency. Okay, and that's the whole idea of MRI, is to flip those hydrogen protons and then watch them as they relax back to the main magnetic field and manipulate that. And that they're flipped by putting little packets of radio frequency energy in. Okay. That causes, I've got these around the wrong way, all good. That causes specific absorption rate. Okay, so what that does is that flipping, the energy that we put into the body that flips those hydrogen protons is absorbed in the body as heat. So the body will heat up. Okay, the more energy that we put into the patient, the more the body will heat up. Okay, and that's called specific absorption rate, or SAR, and it's measured in watts per kilogram. Okay, so that's the energy that we put into the patient to flip those hydrogen protons, and then they relax back. Flip them again and they relax back. Okay. That energy also causes what's called radio frequency fields. So that energy collects into any wires or any let's say wires that are inside or that are around the body. Okay, so let's say we've got a pacemaker wire. When we put in radio frequency energy, that energy is going to collect into a wire. It's going to be attracted to that wire. That wire is going to heat up. Just like the body cells heat up with that energy, that wire is going to act like an antenna and it's going to heat up. Okay? And it's going to heat up so much, it can heat up so much that it starts to burn the tissues around it. Okay? This is the topic that that you're going to do for your assignment. The radio frequency fields, the energy that we put into the patient that heats up causes SAR, and it causes radio frequency effects. So we'll talk more about that later on in the week. Okay. We can reduce the energy. I mentioned that the more radio frequency energy we put in, the hotter the patient heats up, the more the patient heats up. Okay, we can reduce that by reducing a number of things. Reducing the flip angle. We can reduce the number of slices. So instead of doing 20 slices, we do 15 slices. Instead of doing a 90 or 180 degree flip angle, we do a 150 degree flip angle. We put in more radio frequency, we put in less radio frequency. We flip that, we do an angle that's not 180, that's maybe 150, and we put in less radio frequency, which means the patient doesn't heat up as much. We also increase the TR. So instead of putting in a radio frequency like that, we give the cells a little bit more time to relax their energy. So we're going to put in radio frequency over a longer time. Okay, and that gives the cells a little bit more time to relax their energy, or to give off that heat. It reduces the SAR, okay, the specific absorption rate. Okay, so there are three things that we can do. There's a range of things that we can do, including 3 Tesla. 3 Tesla is more SAR than 1.5 Tesla. So if you've got a 1.5 Tesla and you're worried about SAR, if you've got a 3 Tesla and you're worried about heating the patient up too much, put them on the 1.5 Tesla machine. Okay, so the higher the magnetic field strength, the higher the SAR. Okay, core of the body can go up by 1 degree. The head can go to 38 degrees, so 37.7 can go up to 38 degrees. The trunk, the machine will let it go up to 39 degrees, and the peripherals can go up to 40 degrees. Okay, and all this is determined by the pulse sequence and the patient's weight. Okay. Again, the machine calculates how much SAR goes into the patient. So the more SAR we put in, the hotter the patient. The machine will calculate that at the beginning of the sequence. So just like our just like our alternating magnetic fields, the machine will say, okay, you want to do a pulse sequence on someone that's this big. It's going to make this patient, their head is going to get greater than 38 degrees. Okay, I'm not going to start this sequence because the head is going to get too hot. Okay, so the machine will have a cutoff. Okay, it'll say, no, I'm not going to scan this. You have to change something. And so what will we change? We'll have to reduce the flip angle. We'd have to reduce the number of slices. We'd have to increase the TR, and that's not really practical. So we'd have to do one of those things. Okay. All right. To finish off this first session, why is safety so important in MRI? The magnet is incredibly strong. It's never switched off. People who are not necessarily trained to be in the area are involved. So we train all the staff, but we can't train patients. Okay. So we have to say, have you got everything out of your pockets? Have you got no hairpins? Have you got this? Have you got that? Have you got a pacemaker? Have you got aneurysm clips? Da, 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 da. Okay. And a consequence of an error can be severe. People have died due to MRI safety. Okay. And the next slide will show you as a classic example of what that, of what happened in that area. Okay. So have a break. I think, let's go, it's 10:06 now. We'll come back at 10:15 and we'll carry on. So have 10 minutes of rest. I'm going to stop this recording from now. So you can all come back and enjoy. In fact, some might even say it becomes fun. Yeah. Never ever trust a video in your PowerPoint. No matter what happens, it never plays. Fortunately, we have something called YouTube. That has an ad that we can play. Okay. So this is your homework for tonight. I want you to look up YouTube, spend 15 minutes looking at YouTube for all the safety accidents that you can find. It's the best homework you'll ever have. There we are. Can everyone see that?
Yes, we can.
Great. So what they've got there is they've got an oxygen cylinder that's very, very, very ferromagnetic, very, very ferromagnetic, okay? And they've decided to put it inside a magnetic field, okay? So this is torque. You'll see how he's aligning that magnetic field. You see how that oxygen cylinder is, it's not wanting to go into that magnetic field vertically. It's always wanting to align along the bore of the magnet. Okay, and that's exactly how hydrogen protons, that's exactly why we use a magnetic field, to get the hydrogen protons to align along a magnet. Okay, And that's called talk. So I'll go back and shut up. Okay. And you'll never move that, you'll never get that out. Okay. So you just have to leave it, walk away. So this is what happened 20 years ago, almost to the day. A 6-year-old boy died after undergoing an MRI examination. If we have time, we'll go into a little bit more detail about how this actually happened. But basically, he was having a scan and someone brought an oxygen cylinder in and it went straight through his head. Okay, so unfortunately, this is why we're having this talk, to get you guys to understand the MRI safety and understand the physics that's needed before you do clinical next year. Okay, now we'll go back to share our screen because it is incredibly dangerous. Cancel that, we've seen that. So everybody that goes into the room has to be screened, okay? And by screened, I mean, do they have any mechanical implants? Do they have any implants that can cause problems when we take them inside the machine, okay? Everything that they take into the machine, we have to screen them and we have to make sure they're safe, okay? So if I was going to do a scan on someone and you brought a clipboard into the room, there's a good chance that clipboard would fly through the room because you just couldn't hold it, okay? Pens, if they've got magnetic tips on them. Hairpins are the most magnetic things in the world, so never wear hairpins into the MRI machine. Earrings if they're dangly, they can come off your ears and go into the machine. And as you just saw, if there's a patient in the machine, that can cause a lot of problems, okay? Or a staff member, anyone between the implants or the thing that you take into the machine and the isocenter where it's going to end up, if there's anyone between that, it will go to them. So here's an older form, but every participant, every patient who has an MRI machine must fill out one of these forms, okay? Generally what happens is the doctors are responsible. So if the doctor says, I think this person needs an MRI scan because they've got a sore head, they're responsible for checking that the patient doesn't have major implants like an aneurysm clip, a pacemaker, any sort of metal objects in their body, okay? Then they'll send the request form to the receptionist. When the receptionist books the patient in, they'll check, have you got a pacemaker? Have you got aneurysm clips or anything like that in your body? And if they say no, they'll book them in. If they say yes, they might put them to us and just say, is a joint replacement okay? Okay, or whatever they've got. So they'll flag it when they're booking the patient in. And this is a standard procedure for everybody. And then when the patient gets to the centre, they'll fill in this form that states that they do not have a Swan-Ganz catheter. They don't have any surgical clips, wire, sutures, screws, mesh in their body. They don't have a pacemaker, a heart operation, and they'll sign this form, okay? We'll check it verbally with them, and we'll go through and we'll check all the main things verbally with them to make sure that's all correct. We'll sign it as well, and then we'll do the scan, okay? If the patient hasn't filled out this and hasn't signed the form, we will not do the scan, okay? No MRI department will do the scan if that form has not been completed and it has not been verbally assessed with the radiographer. It's too important, okay? So some of the things on that form is orbits. The X-ray, if someone's had metal go in their eyes, it's usually through metal filaments, and they've had maybe welding or grinding, and little metal flints have gone up into the patient's eyes. That could have been 20 years ago. It could have been yesterday. The metal sits away from or may sit away from the nerve, so the patient doesn't know it's there. But of course, as soon as they come into an MRI scan, that metal is going to move or heat up. Okay, so it's very important that they do not have an MRI scan. If we're concerned, if they hadn't been removed by a doctor, we do an X-ray to see or to make sure that that MRI machine, that metal hasn't stayed in their eyes, or they don't have any metal in their eyes. Okay. Pacemakers. So this isn't true. Mechanical devices, they are MRI conditional. That means that pacemakers can be scanned, or the later models are MRI conditional. So, gosh, making my notes as I go, changing it as I go along. The later models are usually MRI conditional, okay? And that means that there's certain conditions that we must follow. We must have a cardiologist. We must have a backup medical plan. We must have a technologist that can turn the pacemaker into an MRI safe mode. They're not necessarily safe, just safe, okay? They're conditional, so we must have contingencies in place, and there's quite a lot of work to be done with patients who have pacemakers or defibrillators, okay? They also have wires. So we mentioned that when we start the MRI machine and when we put in that radio frequency, or when we put that radio frequency in, that radio frequency collects in the wire and that wire can heat up, okay? So it's very important that we check the wire to make sure that wire is MRI conditional. So it's not going to heat up and it's not going to burn the patient, okay? So MRI pacemakers. So pacemakers, the later models are generally MRI conditional. So they can be scanned, but there's a lot of work that's involved to get them scanned, and we have to check and make sure everything that's inside that patient, or that's it, the pacemaker, the defibrillator, and the wires are all MRI conditional. Aneurysm clips are usually safe. They are the older models were ferromagnetic, but we must look up the make and model of the pacemaker clips, okay, of the aneurysm clips. Make sure that they aren't the older models and that they are made of material that is safe, okay? Also, aneurysm clips and other little implants like this may, if that spatial gradient is too great, so here it's like the clips may be rated to 10 Tesla per meter. Okay, so that means that the patient cannot go into this machine because this machine has 15 Tesla per meter. Okay, so we know that the higher the spatial gradient, the more force on that aneurysm clip. So if that aneurysm clip went around this area of the magnet, there's a chance it would pull off the blood vessel. Okay? So it's very important that if it was an urgent scan and we had to keep the patient in and they had an aneurysm clip, this aneurysm clip only stayed in the very middle of the magnet, okay? Or put it on another magnet that has maybe a maximum gradient of 10 Tesla per meter, okay? If that aneurysm clip had a maximum field of 10 Tesla per meter. Don't stress too much over that if you don't understand it. What I'm basically trying to say is that a lot of the devices, they may be safe up to a certain rating, a certain spatial gradient, okay, and magnetic field strength. So cochlear implants are mechanical devices. Okay, so they'll change their working when the patient experiences a change in magnetic field. When the patient goes into the room and experiences the main magnetic field, exactly the same as you take in a watch or a mobile phone. It sets up a current inside the device. Okay, Stapes implant they're little tiny bits of metal that can move or turn and talk inside the body or inside the middle ear where they are, and then that's going to cause a lot of damage. Okay, I mentioned the grafts and the stents, how they can turn. Pregnancy, we try not to scan in the first trimester of pregnancy. Okay, and that's because we don't have any definitive evidence that it is safe. But there's no evidence that it's not safe, and departments are more and more putting patients in earlier and earlier in their pregnancy because there's no known side effects. But as a precaution, we try not to put patients in their first trimester. After that, we don't put patients in. After that, oh my gosh, I'm getting tired. After that, we can put patients in the machine. In second and third trimester, we can put patients in the machine. Okay. We don't give contrast to patients, okay, who are pregnant because we don't know how much goes to their baby. But breastfeeding is okay to have for contrast. We have devices inside the body that will program, that they use a magnet to program. So because, as shunt is an example, because they don't want to go in and operate every time they put a shunt in, every time they change a setting of that shunt, so they'll use a magnet to position over the pacemaker or over the shunt, and they'll reprogram the setting. So of course, if we expose that patient to a strong magnetic field, that's going to reprogram the setting. Okay. We know that bullet wounds are metal. Okay, so that can move inside the body. Renal impairment is for contrast. We'll discuss that later on. We won't talk too much about that. Swan-Ganz catheter, there's implants in the body that can melt. because of the metal in them. Penile implant, there's two types of penile implant that are very, that can be dangerous inside the MRI. They can cause a lot of pain. Tattoos have small amounts of metal in the ink, or they can contain small amounts of metal in the ink. Okay, so that can heat up. It's not a strict contraindication, but we just have to be aware that that can be the case. Okay, and they can also cause artifacts. Dentures can cause artifacts, so we try and take them out if they've got any metal. Joint replacements are generally okay. So you break your leg and you've got a pin or a plate in your leg, an ORIF. They're generally okay because they're made of titanium and they're not magnetic. They may cause an artifact, so we want to know about it, but they're generally okay. The other reason they're okay is because they're in the bone and they're solid and the bone's grown around it. So if they've just been put in, then it's best to wait 8 weeks until the bone's grown around it and they're held in place. Okay, I'm going to skip this for now because we're going to run out of time. I've been talking too much as usual. We can have allergies to gadolinium. Acoustic noise, we always use headphones and earplugs on every patient and every staff member that has to go in the room when the machine's on. They always have to have hearing protection. We always watch the patient, We give the patient a little buzzer, okay, because the machine's noisy. We can't hear them when they yell out, or if they yell out. Hopefully they don't. Okay, if they're sedated or unconscious, we always use pulse oximetry. We always watch their heart rate and make sure they're okay. Okay, I mentioned claustrophobia. Okay, so quench is another important aspect, and we're just about there now. We'll talk a little bit about contrast. Yeah. Quench is another aspect of safety in this machine because I'm not sure whether you've done it in your physics yet or not, but we use a superconductive magnet. So what happens is those coils are bathed in liquid helium. Liquid helium's, I think it's about minus 270 degrees Celsius. So we know that if we didn't use liquid helium, we energize these coils, and those coils, the energy goes around in a circle. Okay, eventually it's going to heat up and eventually it's going to get resistance and that energy is going to stop. Okay, start it again, next energy comes in, goes around, heats up, resistance and stops. So what we want to do is we want to bathe these coils in liquid helium. What's going to happen then is that energy is going to keep going round and round and round. It's not going to heat up. The current's not going to heat up and it's not going to stop, okay? So the machine's actually a superconductive magnet is a very, very cheap machine to run because essentially it's got the liquid helium keeping it cool. It's got the energy going around in a circle. That's it, okay? That energy or that current going around in a circle causes the magnetic field that we know through your physics. And that's what causes the main magnet, okay? Unfortunately, what happens if we want to quench? So quench is when we can automatically stop this machine, okay? We hit a quench button and we can release the liquid helium. So these wires will heat up. And of course, as soon as they heat up, they get resistance and the current stops. When the current stops, the main magnetic field in the middle stops. Okay, so how do we heat that up? We heat that up by releasing the helium, the liquid helium around those coils. So we heat that up a tiny little bit, and then that liquid helium turns to gas, and it goes through a vent. So there's a vent that's up here, goes out to the atmosphere, out of the machine. Okay. Unfortunately, the liquid helium, when it turns to gas, expands at 700 times. Okay, so that's incredibly, that's a lot of gas. All right, and that's why we must have a working vent, and they must check that vent regularly to make sure that it's not blocked. Okay, but if there's an earthquake or if there's something that happens to block that vent, that gas can come in the room and cause a lot of pressure inside the room. It's happened only a handful of times in the world. As I said, usually what happens is that liquid helium turns to gas, it goes through the quench pipe and out into the atmosphere. Okay, the machine ramps down, so we go from 3 Tesla to practically 0 in 10 seconds, and we get the patient out. The only reason we would quench this machine is in a medical emergency. Okay, so this happened at Monash Medical Centre. A cleaner took a floor buffer into the machine, and the floor buffer, of course, got stuck to the back of the MRI machine. Okay, so of course we wouldn't quench the machine, we wouldn't stop that magnetic field in an emergency because it's not an emergency. Okay, whereas if the cleaner was stuck between that floor buffer and the machine, we would have to stop the magnetic field, okay, to get him out. That's a life-threatening situation. If we stop that magnetic field, it would cost about $260,000 to start it again. Okay, so that's a lot of money. So that's why we don't stop that magnetic field when we come to work and we see that the floor buffer's been stuck in the magnet, or that the chair's been stuck in the magnet. Okay, we don't stop that. We don't quench that machine. Okay, because that costs too much money, and the engineers come in, they take that current down very, very slowly, and then they take the magnet, then that reduces the magnetic field. They take the chair out, and then they re-ramp up the magnet. So they put the current back into the magnet, called ramping. Okay, and then they ramp up the magnet and that becomes stronger again. Okay. However, if a patient or if someone was stuck by an oxygen cylinder, then you would have to quench the machine. Okay, so someone's brought an oxygen cylinder into this machine and they have to quench the machine, okay, to get that man out. Okay, and get his friend out because his friend is stuck by that oxygen machine as well. Okay. Unfortunately, this incident happened in America a couple of years, this incident happened in India a couple of years ago. And what happened was the engineers had disconnected the quench button. So the quench button didn't work. So it cost them about it cost them, so I'm not thinking. So it cost them it took them about 4 hours to get another engineer in and work out how to quench the magnet when this person had brought in an oxygen cylinder. Okay, so it's very important to have that function. But if it's not a life-threatening situation, we don't have to quench. We shouldn't have to quench. Okay. Does this play? No. I don't have permission to play my own slide. All right, I think that's just another oxygen model. that you're going to look up for your homework anyway. Now, what I might do is I've just pretty much finished my talk. What I might do is I might go through this incident here. So I'm going to leave you to read this and what would be great if people could tell me what went wrong. So what things in there went against what I've been talking to you about this morning. Okay. How could this oxygen bottle incident have been avoided? All right. So I'm going to give you 5 minutes. Have a read of that. The sun's shining in my room, so I'm going to go and open my window. Have a read of that, and we'll talk about it in a minute. And I want you. Another minute. Has everyone read it? Has anyone not read it? Is anyone still here? Or have you all gone outside? Okay. Perfect. Tiffany, well done. Okay, so I'm just going to stop sharing and I'm going to share. I'm going to stop sharing and now I'm going to start sharing. Okay, so now you've got my Word document. What Tiffany mentioned very well perfect. Okay, so both of the technologists on duty left the console to try and resolve the problem, leaving the access to the magnet room unattended by trained staff. Okay, that's our first thing. Anything else? What else happened that that perhaps shouldn't have. Anyone? Anyone?
Both of the radiographers left the room and there wasn't anyone MRI trained there.
Yep, perfect. Perfect. What else? What else happened to cause that machine?
Somebody boarding a oxygen cylinder.
Bingo, well done. Perfect. That steel cylinder was brought into the magnet room where the MRI pulled it from grip of whoever was carrying it, and it thrust into the bore of the magnet. What else? What else perhaps would have happened or would have stopped this from happening if it didn't happen? I can see 5 or 6 things there at least.
The oxygen should have been piped through the hospital supply
Perfect.
main system.
Yep. Excellent. An independent storage cylinder. Let's go from that one. Perfect. So an independent storage cylinder. So it obviously wasn't checked. Okay, so if that was checked and if that was through the hospital supply, absolutely, good one. Anyone else?
The oxygen wasn't connected to the central alarm system. So like when it cuts off, no one would know that he's not getting a sufficient supply.
Perfect. Okay. Have I done that? Wasn't part of the hospital's main system. Okay, I think central alarm system. Excellent. Great. Great. What about the behaviour of the anesthesiologist, or the anaesthetist? What about the behaviour of him?
Would it be that there's no point screaming because the machine's going to be really loud?
I think he was screaming for oxygen just because he was panicking.
Mm.
Perfect. Well done. Yep. And I suppose we can highlight this one. As the level of panic escalated. What else? Very close to that. Can someone point out the next sentence?
A random staff came to the MRI room.
Okay, good. So a hospital staffer. So a hospital staffer, no training. Okay, so the staff that worked in there weren't training or weren't trained in that environment. Perfect. And the next one.
And they just happened to have a portable oxygen cylinder in the room.
Exactly. I'm good at this. Okay, so we don't put portable oxygen cylinders around the MRI room for exactly this reason. Okay, you won't find a portable oxygen cylinder around an MRI room. It must be, when we bring patients from the ward, they can be on the cylinders, but then they have to be transferred and the cylinder gets straight the way the hell out of there. Great, good. Anyone else? I think we've covered most of it. Oh no, I can see one more. This is sort of clutching at straws, and not always true, but the boy was having difficulty breathing while receiving the scan. So we never like to scan patients who are unstable. Okay, so we always like to keep them, because MRI, you have to monitor the patient from a distance. You can't get over the patient. Okay, so we don't like to scan unstable patients. That doesn't mean we don't, but you can see what happens there. You can see that there's a problem there if the patient crashes. Okay, MRI is not the modality that we would use to scan an unstable patient. And on one of the last points, probably one of the most important slides of all I missed, was if there's a patient inside the room and they do stop breathing and they have a code, the first thing we do is to get the patient out of the room. Okay, so we've got these pedals, we've got these, where are they? We've got these pedals, okay, to disconnect most tables, get straight out of the room, we shut the door, and then we call for a code, okay? So we never leave the patient in the MRI scan while they're not breathing, or if there's a medical emergency, we get the patient straight out of the room, lock the door, and then we call a code, okay? There's been countless times where we've called a code at the hospital and doctors and nurses have come in with all their equipment and the patient's not fully out of the room. And it's a nightmare. Everything goes everywhere, okay? And you have to say to them, you're not going in to see your patient. You're waiting at the door until we get the patient out. And that's not productive because they don't know, doctors and nurses don't necessarily know that machine's on all the time, okay? So every department will have a policy that if the patient crashes, you get the patient out of the scan room, you close the door, and then you call for the doctors, okay? Tiffany, exactly, perfect. I've just read your post, and you would remove the patient from the magnet room if they are in that level of distress. I hadn't even thought of that, but that's exactly what you should do. Absolutely perfect. Yeah, okay. So I think we've done our 2 hours. We didn't get time to do the extra stuff, but we'll do it next time. I'm sure we'll do it in the next year or so. I had a couple of questions. I had a couple of just pathology slides and babies and implants. So this is an aneurysm clip that's inside the patient, okay? It's actually a safe aneurysm clip because an unsafe aneurysm clip would cause a lot more artifact.
Hi, Richard. We can't see the PowerPoint. It's still in the Word docker.
Oh no! I've just spent 5 years. I've just spent 5 minutes talking to myself. Let's have a look. Okay, so what did I do? I just mentioned that there's pedals here to get the patient and the table outside of the room. Okay, click that, get the patient out, click that pedal, get the patient out of the room, close the door, we're done. Okay. We did just go through that slide, so we should be all good with that. And I was just going to say, as a wrap up, we get funky pictures. Okay, we do get good pictures. So get excited. We get pictures like that if we want to. We don't just get pictures, we can get spectroscopy as well. That's MS, advanced MS that you see on the brains. We've got babies headbutting each other. And there's an aneurysm clip. Okay, so even though that's safe, we decided that was safe in this machine. If there was a ferromagnetic aneurysm clip, the artifact would be a lot greater. Okay, but as it stands, that's all there is to it. Okay, so we're done today. Can you guys tell me, do you have another lecture now?